I'm Xiang from Xi'an Jiaotong-Liverpool University. I'm glad to present the paper exploring visual techniques for boundary awareness during interaction in augmented reality head-mounted displays. First, the background. Hand-based interaction is one of the most commonly used interaction methods in augmented reality head-mounted displays because it's assumed to be natural, practical, and easy to use. As you can see, consumer AR headsets like Meta 2, Magic Leap 1, HoloLens all have enabled hand-based interaction. Currently, there are many issues in hand-based interaction. For instance, when you're holding your hand in the mid-air for a few minutes, you may suffer arm or hand fatigue. And the way interacting with virtual objects are unnatural sometimes, for example, selecting a distant object. Also, hand-based interaction normally does not provide any feedback to the users unless you are wearing some types of external haptic devices. These issues are all widely studied. However, boundary awareness issues in AR devices have received little attention. In AR HMDs, the supported chat interaction volume is relatively small and limited. Due to this small chat area, users often observe that the visual object may not be responding to their gestures during regular interaction, or observe that the visual objects are partially disappeared. One way to avoid or mitigate this issue is by allowing users to see via explicit visual cues the chat interaction area. Our work has two contributions. A first evaluation of systematic exploration of visual methods for boundary awareness in AR HMDs. Results of a user study comparing different visual boundary awareness methods for interacting with visual objects in these systems. Here, we present the methods that we evaluate in our study. Please refer to our paper for more details. Due to the lack of related work, we did a formative study to examine the challenges that a user might face when interacting with AR HMDs without boundary information. Then, based on the participants' comments, our observation and interviews, we proposed two preliminary solutions to visualize the interaction boundary of AR HMDs. One is an off-body indicator, that is, mimics Oculus Rift. The other one is an on-body indicator, that is, mimics Meta 2 AR HMDs. To understand how to provide such boundary awareness methods and their usefulness, we explore our preliminary solution to be provided statically and dynamically. Static surfaces. This condition provides a visualization of the interaction area in the form of planes or borders. The surfaces are shown in blue but with 40 opacity to allow users to still see through them. Blue is selected because it works well in indoor environments with white walls, which is our experimental environment setting. Static coordinate lines. In this approach, as long as the user's hand is inside the interaction volume, the distance to the volume surfaces is shown through a 3D coordinate axis. The position of the coordinate center follows the hand position. The length of the line indicates the distance to the boundaries. This condition visualizes the surfaces when the user's hand only gets very close, that is 1.5 cm to the corresponding boundary. This condition is analogous to the static coordinate line. The only difference is that the system only visualizes the coordinate lines when the user's hands get very close, that is 1.5 cm to the corresponding boundary. In this condition, no visual feedback, which represents the case of the current way of interacting with AR HMDs. It acts as the benchmark and baseline comparison. Now I'm going to describe the experiment. We employed a one-way within subjects design with 20 participants. The 5 conditions are shown in the slides. Here are sample test bed environment for the 5 conditions. The interaction volume is 25 centimeters times 20 centimeters times 16 centimeters. It is placed at 42 centimeters in front of the user, as Magic Leap 1 can only display visual items about 40 centimeters away from the user. Users could only perform interaction when their hand is inside the interaction volume. There are 8 cubes placed inside the interaction volume as target objects, and 4 are outside the interaction volume. That is, 12 centimeters away from the surface and is outside the actual visual FOV of the Magic Leap 1 as target translation locations. During the experiment, one cube would randomly change its color to become the target. Users could use their index finger to target the cube they want to select and select it by using a palm open gesture. The color of the cube would be changed back to the default color, and the target location would appear when the selection of the cube was made successfully. To complete the task, the user would need to drag the cube and drop it on the target location, that is, hitting the center of the cube in the target location. A wrong selection did not cause any effect while an error, that is, dragging the cube and hitting the boundary, would stop the cube from moving. We measured task completion time, the number of arrows for task performance. The task completion time was the translation time from the first successful selection of the cube made by the participant to the time when the cube was dragged and dropped at the target location. The arrow was the number of the times the cubes hit the boundary as the participant's hand was not rendered by the AR system, that is, moving outside of the boundary. For users' performance, we measured system usability, users' experience, task workload, arm tiredness, and vision tiredness. At the end of the experiment, we also collected comments and ranking of the techniques. 20 participants were recruited from a local university campus. None had prior experience with the Magic Leap 1, which is the device we use in the experiment. The experiment was conducted in a university lab. Here is the part of results. The analysis showed the technique had a significant effect on the task completion time. Post-hoc tests confirmed a significantly lower time for the DS compared to the DCL. We conducted a Friedman's ANOVA where the analysis yielded a significant effect of technique on errors. Post-hoc analysis showed that DS had a significantly smaller number of errors than DCL. The analysis yielded a significant influence of technique on mental workload. Post-hoc tests confirmed that SS caused a significantly lower mental workload than DCL and benchmark. There were no significant effects of technique on users' experience, arm fatigue, visual fatigue, and system usability score. Here is about the ranking. Finally, the conclusion. All in all, based on our results and users' feedback, we suggest that use a surface-based technique over benchmark, as the technique could help users to know the boundary visually to get their interaction. Use coordinate line-based technique over surface-based technique. If users feel that their view is occluded and the interfaces with their interaction, boundary awareness methods should be provided use-dependent. Some participants made over 100 errors with the benchmark technique but have no issues interacting with any of the boundary awareness methods. It should be tuned to suit the individual's needs and predispositions. Providing boundary awareness methods by default. This is because during the phase where participants tried the AR device to get to know it, we observed that novice users tend to overvalue the FOV of the AR HMD. They would ignore the FOV of the AR device and assume that the interaction would be the same as what they would typically do during actual tasks. It could be disabled when users think they could do without it. We only test one-handed gesture during the experiment. Future work can explore whether our findings will also be applicable to two-handed gesture-based interactions where large motions are required. Several values used in our experiment are predefined fixed values due to the lack of related private work. Future work can implement a dynamic color changing scheme for the surfaces to suit the background. We only tested object translation task, which is only the starting point. Future work could include other common manipulating tasks in 3D environments, for example 3D modeling. We only propose evaluate visual methods. Future work could explore other primary sensory channels like sound and haptics on boundary awareness. That's all, thank you. Please read our paper for more details of this work.